Okay, so this is video number 3 out of 4, and we're going to take a look at activity 10-1 omnibus F test. Again, the name omnibus F test, it means that we're running the t-test for the overall difference. As compared to, in the next video, we're going to discuss pairwise comparisons, which is a different kind of a test. So this is the omnibus F test. And so this is the kind of information we obtained from activity 10-1, SST equals 46, SSB equals 30, and SSW equals 16. And so the 4 steps: first, no hypothesis and the alternative hypothesis. So no hypothesis, mu1 equals mu2 equals mu3. So there's no difference whatsoever, and the alternative hypothesis says not all mu's are equal. So somewhere there may be a difference. So not everything is equal. Okay, so that is the alternative null and alternative hypothesis. Next, we need to determine the critical F value. Now, let's see. So remember the degree of freedom that we have for, we estimated in the previous setting, SST equals degree of freedom total equals 14. So it's n minus 1. 15 subjects subtract 1 equals 14. Then degree of freedom for between. How many different conditions do we have, right? df of b. That equals k minus 1 number of conditions minus 1. So 3 minus 1 equals 2. And lastly, the degree of freedom for within. dfw equals n total number of subjects minus the number of conditions. So that's 15 minus 3 equals 12. Okay, so we have 2 and 12 degrees of freedom. We kind of need that information. So F, we're talking about 2 degrees of freedom for between group and 12 degree of freedom for within group. And we can either use our F table or we can use the distribution. So we are going to use the distribution. So let me exit from this screen just for a second. Let's see. Discard. So let's take a look at the website. Okay, so right here under important concepts, and there's a link for the F distributions. Okay, so if you click on the link, one thing you notice is that first thing you need to do is to specify the degree of freedoms. So in this website, it's called the degree of freedom for the numerator. So they're talking about SSB, that's 2. And for the denominator, because when you calculate the F statistic, it's variance between groups divided by variance within groups. So within group variance is the denominator. Okay, so that's the degree of freedom. Sometimes we call that as the error degree of freedom. So that's 12. Okay, so we have 2 and 12 degrees of freedom. It's always the right tail. And so P equals 0.05, meaning at alpha equals 0.05, so F value equals 3.885 or 3.89. Either way is fine. So that is the critical value of F statistic. Right, so let's go back to here. Let's do this again. So P equals 0.05, F equals 3.885. So that is a critical value of F. And this is the region of rejection, which defines a 5%. And remember, under the alternative hypothesis, F is expected to be greater than 1. So a large F value always indicates the more higher likelihood that to reject the null hypothesis. So the region of rejection is always on this side. It's one-sided. However, the test itself is always non-directional. It's a non-directional test. Now, the reason is that if you think about how f is calculated, it equals variance, right? So this is a variance. And in the context of ANOVA, we call that MS, mean squared between, divided by mean squared within. And how do we obtain the mean squared? Well, it starts from sum of squared divided by degree of freedom. And how did we calculate the sum of squared? We took the deviation, score deviation from the mean, and we take the square. Now, once we take the square, we got rid of all the information, any information that we have about the direction of the difference. So in the F statistic, we actually have no information. We have no information about the direction of the difference. The only thing that we have is how much difference is there, or there is. Okay, so that's why F-test or ANOVA is always non-directional. There's no such thing as one-sided or one-tailed F-test. It's always two-tailed. It is always non-directional. Okay, so next thing that we're going to do is calculate the test statistic and complete the ANOVA summary table. So this is how we organize the information when you conduct analysis of variance, the omnibus test, F-test, source of variation between groups, within groups, total. And then SS, sum of squares, degree of freedom, mean squares, F, and p-value. So this is called the ANOVA summary table because this is a table very neatly combines all the information that we need for the significance test. So I already have some of this information. SS between equals 30. SS within equals 16. SS total equals 46. Degree of freedom between groups, 2. Right? That's 3 minus 1. And the total equals 14, that's n minus 1. And within group, that's 14, no, that's, 14 n minus k. So n minus k equals 15 minus 3 equals 12. Okay, so we have sum of squares and we have degree of freedom. Now, in the context of analysis of variance, variance is not variance. Variance is called MS, mean squared. This is what we call variance in this specific context. Okay, so MS B equals, this is the sum of squares B divided by degree of freedom B. So you notice the sum of squares divided by degree of freedom, that's how we calculate variance. And this is variance. It's a variance by a different name. So 30 divided by 2 equals 15. Okay, so MS between equals 15. Next, we're going to calculate MS within. So MS W equals SSW divided by degree of freedom W. So that equals 16 divided by 12. Okay, 16 divided by 12, 16 divided by 12, so 16 divided by 12, 3, 8, that's 6, that's 4 over 3, that's 1.33. Okay, so equal, we just round up to 2 decimal points, 1.33. So this is 1.3 and 3. There's no need to calculate the total variance. We just cross it out. Next, we're ready for the F value. So F equals MS. So variance between group, right? So that is variance caused by both treatment and error, divided by variance due to error itself. So that's MS within. That equals 15 divided by 1.33. Okay, so 15 divided by 1.33. Probably a calculator. So let me use keep. So if we grab where is my, here we go. So let's see, 15 divided by 1.33, that equals 11.28. So that equals 11.28. Okay, so that's our F value equals 11.28. We don't need anything here. We don't need anything here. And then there's a p-value associated with 11.28. So for that, we have to go back to the F distribution. Keep everything. And we're going to switch back to this distribution. So we have 11.28. So if you type in the F value, this website gives you the p-value, 0.002. Okay, so F equals 11.28. So it's right here. P equals 0.002. So remember that we discussed that a large F value provide evidence to reject the null hypothesis. So 0.002. So let's take a moment to think about what exactly 11.28 means. It means that the variance caused by treatment plus error is more than 11 times that of the variance caused by error alone. Okay, so which means there's likely to be a treatment effect. In fact, we have a p-value equals 0.002, meaning if the null hypothesis is true, if there's indeed no difference whatsoever, then the probability to obtain the data that as extreme as we observed in this case is less than 0.002, which is a very, very low probability. So our conclusion, we reject the null hypothesis and conclude that somewhere there is a significant difference. Okay, so there's that. And then here is also a good point for us to calculate the introduced effect size. So the effect size that we could introduce here is called eta squared. So if you type it up, you have to insert a special symbol. It's the Greek letter eta. So eta squared equals sum of squares between groups divided by sum of squares between plus sum of squares within. In other words, sum of squares total, right? So this equals sum of squares between is 30 divided by 30 plus 16 is 46. So that equals 30 divided by 46. It's a very, very large effect. So almost 0.6, not quite 0.6. So I'm just going to, so you can calculate the actual number, but I'm just going to give you a very rough number, which is around 0.6. Let's do the calculation. So 30 divided by 46. So 30 divided by 46. 0.65. Okay, so it's 0.65. So the effect size measurement, according to our calculation, equals, let's see, where is my pen? So equals 30 divided by 46. So this is SST, right? This is the SST. Equals 0.65. So what does this eta square indicate in terms of measurement of effect size? Here's something. So here's what something that you can think about. So let me see. I'm actually going to let me do this. Keep. So I'm going to insert a blank page. No, new slides. Let's do this. Okay, so think about what exactly this eta squared is as a measurement of effect size. Now, previously we talked about a cons D. So what is cons D? When we think about cons D, we always think in terms of two distributions, right? So cons D is the distance between these two distributions and measured by the standard deviation. So how many standard deviation they are apart. That is a measurement of effect size if we conduct a t-test. Now we are conducting analysis variance. So this no longer apply because there can be 3, can be 4, can be any number of distributions. So that we can't measure effect size in this way. So instead, we have something called eta squared. Eta squared is SS between. So this is treatment plus error divided by SST total. In other words, it's a proportion. So if you draw a circle and use this circle to represent, let's say this entire circle is SST. Sum over squares total, the total amount of variation in the data. SSB is a slice of that. So it's a proportion of the total variation that can be attributed to the treatment and error or between group variation. So this is SSB. It's a proportion. Okay, so it's also a very intuitive measurement of effect size. It's a proportion of total sum of squares that can be attributed to between group variation. And 0.65, 65%, that is a very, very strong effect. 65% of the total variation in the data can be attributed to between group variation. Okay, so anything that's beyond 20%, 15, 20% is actually considered a large sample size. So, a large effect size, not a sample size, effect size, a very large effect size. So in this case, eta squared equals 0.65. We are looking at a very large effect size. Okay, so this is the end of this video. And in the next video, we are going to talk about go over the activity 10-3. We will talk about a number of things: post-hoc comparisons, interpret SPSS output, and how to write the results in APA format. Here's an actual precursor. This is the APA style table. So you will say something like, first, you specify the analysis, right? So one way between subject analysis variance was conducted with phone type as the independent variable and driving performance as the dependent variable. So the first sentence describes analysis. Second, the conclusion. The effect of phone type was significant. F212 equals 11.25, P less than 0.05. You might say P equals 0.002. This is actually better to do it this way. So report the precise value of P. So P equals 0.002. And in parentheses, you will say see table 1. And then you attach the table towards the end of your writing. And according to APA style, table has to start on a separate page. So what you want to do is to insert a page break. So you start table 1 on a new page. And then there's a bunch of things that you need to do in terms of APA format for table. So table number is always in bold. The heading for the table is always in italic, and it's the up and the lower case. And the table, the only thing you have are the horizontal lines, so there is no vertical lines. Okay, and you provide the mean as a number of participants in each condition. That's the mean, and by convention, you put the standard deviations in parentheses. So that's the standard deviation, standard deviation, standard deviation. And this is the total standard deviation. And you add a note. Note, the word is italic. But the note itself is not italicized. So those are kind of those peculiar things about APA style, APA format that you just need to get used to. Okay, so you would say, note the numbers in parentheses are standard deviations. So you tell people what those numbers are. Okay, so that is the end of this video, and we have one more to go, and then we're done.